Hey, the YouTube is about to put out here with another Veritasium video. Today we got something strange happens when you trust quantum mechanics. Let's get right into it, shall we? Hit it.
As a 42-year-old who's spent most of my life studying physics, I must admit that I had a big misconception. I believed that every object has one single trajectory through space, one single path. But in this video, I will prove to you that this is not the case. Everything is actually exploring all possible paths all at once.
Isn't this like the whole video he did in the past where it's like, we've only measured the one-way speed of light, the two-way speed of light, and we don't know if the speed in one direction is like twice as fast as the other direction, or is it half the time in one direction versus the other side. You feel me? It's kind of a weird concept, but this is kind of intuitively hard to explain, so I'm curious. I'm very curious where he's going with this.
So let's start with a simple thought experiment. Say you're at a beach when all of a sudden you see your friend struggling out in the water. You want to go help him as quickly as possible, so which path should you take to get there? The shortest path is a straight line, so you could head directly towards him, but you can run faster than you can swim, and this path requires more swimming. So alternatively, you could run down the beach to minimize the distance through the water. But now the total distance is longer than it needs to be.
Well, yes, technically, because your limitation here is the time needed for you to get from A to B. So while you could say A to B is the shortest distance, this would be the fastest time to target. So I think it depends on the way you frame the question, I guess. But yeah, this would be the most optimal solution for sure. Sure.
So the optimal path, it turns out, is somewhere in between.
Sure.
To be precise, it depends on the speeds at which you can run and swim. Now, you might recognize this mathematical relationship because it is the exact same law that governs light passing from one medium into another.
Oh, okay. Oh, this is interesting because this is, I think, wasn't it Lenz's law? Or because it's between the two interfaces when light goes from one medium to a different medium. Okay. Okay.
So light also takes the fastest path from point A to point B. What's weird about this is that as humans, we can see where we want to go and then figure out the fastest route. But light? I mean, how does light know how to travel to minimize its journey time?
Ooh. I mean, intuitively, I think it's because of the physical nature of the property and the medium it's going into, as in like light naturally tends into this deviation because it's the physical property of the medium it's going into, is how I think we were explained in college and in school, basically. I mean, it's not like light has consciousness to know clearly the optimal solution, and it's not calculating every time it goes through different mediums, you feel me? So there probably is some physical aspect of the universe that's giving it that, that pathway, basically. This is how I imagine it.
Now, here is where my misconception comes in. I shine a laser beam. The light just goes in one direction. I throw a ball. The ball just goes in one direction. I would have answered, there is nothing strange about this. Light sets off from point A in some direction, and then a little while later, it encounters a new medium. And due to local interactions with that medium, it changes direction, ending up at point B.
This is how we were explained as well. The natural phenomena that happens when you have light traveling between different interfaces, it just happens to be a physical property of the medium it's traveling in. This is how we were explained it. Unless there's something...
If you later find that of all the possible paths, light took the shortest time to get from A to B, I wouldn't think it was optimizing for anything. Right. I would just think that's what happens when light obeys local rules. Right. But now I will prove to you that light doesn't set out in only one direction. Instead, it really does explore all possible paths. And the same is true for electrons and protons, all quantum particles. So the fact that we see things on single, well-defined trajectories is, in a way, the most convincing illusion nature has ever devised. And the way it works all comes down to a quantity known as the action.
Oh! This is from an older video, okay.
In a previous video, we showed how an obscure scientist, Maupertuis, made an ad hoc proposal that there should be a quantity called action, which he defined as mass times velocity times distance. And he claimed that everything always follows the path that minimizes the action. Hamilton later showed that this action is equivalent to the integral over time of kinetic energy minus potential energy. Action was useful and an alternative way of solving physics problems, especially when Newton's laws get too cumbersome. But then, around the turn of the 20th century, action showed up at the heart of a scientific revolution, the birth of quantum mechanics. It all started with electric lighting in Germany.
Think about what it's like in the 1890s, right? Electricity being more widely available, at least in urban centers, and things like, light bulbs. They were new. They were literally the hot new thing.
Germany wanted to replace all their gas streetlights with electric light bulbs. So an important question was, how do you maximize the visible light given off by a hot filament? Scientists at a German research institute, the PTR, studied how much light different materials emitted as a function of temperature. At low temperatures, each material gave off its own characteristic spectrum, mostly in the infrared. But above about 500 degrees Celsius, all materials started to glow in the same way, with an almost identical distribution of light. The hotter the object, the more energy was emitted at every wavelength, and the peak of the distribution shifted to the left.
But they still didn't understand how it worked theoretically. So that was sort of the next step, right? Because if you can understand how it works theoretically, then you can use that theory to potentially design new products.
They started by imagining the simplest object possible, one that would absorb all light that falls onto it, and perfectly emit radiation based on its temperature.
Okay.
They came up with a hole in a metal cube. This hole is a perfect black body because any light that shines onto it will go straight in, bounce around inside, and eventually be absorbed. But this also makes it a perfect emitter. Any radiation inside the cube can escape through the hole unimpeded. Theorists reasoned that electrons in the walls of the cube would wiggle around, emitting electromagnetic...
I just want to pause right there because we were taught what a black body is. We were never taught that there was a practical example of a black body. Like, we always had the principle that it's a perfect emitter and absorber of radiation, sure. But we always assumed it was how do you say, it's a hypothetical object. No one actually told you that there's a practicality in the object when you can just take a metal cube and put a hole in it. That would have made things a whole lot easier to understand, actually, to be fair.
Waves. These waves would then bounce off the other walls.
And let me guess, destructive interference, some of them are removed off. The only ones that are left are like what? The constructive waves, I guess? Wouldn't they also kind of destructively interfere? Huh.
When you have two waves of the same frequency, where one travels to the right and the other to the left, they can interfere in such a way that they create places where there's no wave amplitude, those are nodes, and places where there's maximum wave amplitude,
sure,
the antinodes.
Sure.
Waves like this are called standing waves because they don't really move left or right. And inside a cavity, given enough time and reflections, it is only these standing waves that survive. All the other ones just cancel out.
Oh, that is fascinating. You always assumed a wave would be moving back and forth, but just having waves... I mean, okay, I can imagine, given enough time, it just in the same position and over again. That's interesting, okay.
So a sort of order emerges from the chaos.
I mean, sure. This is the same argument for like those, the timing machines that go back and forth, and you put them on top of a non-steady surface, and I think it's pendulum, right? The pendulums. So if you put them in, different orders, and then like say 2 or 3 of them on the same unsteady surface, you let them go, eventually they destructively interfere so much that all that's left is the ordered, back and forth movement. Like that's fair enough. We saw it in an earlier Veritasium video. I can see the same principle here, in theory, in a smaller scale.
In 2 dimensions, standing waves look something like this.
Okay.
For shorter wavelengths or higher frequencies, you can fit more and more different vibrational modes inside this cube.
Okay.
So that in 3 dimensions, the total number of modes is proportional to frequency cubed, or 1 over lambda cubed.
Okay.
The expectation was there would be more and more waves inside the cube the shorter the wavelength. This led directly to the Rayleigh-Jeans law. At longer wavelengths, it matched the experimental data pretty well. But at shorter wavelengths, the theory diverged from experiment. In fact, it predicted that at the shortest wavelengths, an infinite amount of energy would be emitted.
This would be the ultraviolet catastrophe, right? Like every physics student, like it's not even physics. If you generally take engineering, even to I think a high school or even college level, this is taught. I think it's one of those.
This, for obvious reasons, became known as the ultraviolet catastrophe.
Right. The way they solved it was by the quantization of energy. Basically, they call it as packets of energy. They had to kind of put it there. Right. Again, this is what we were taught. So I can recollect this is what we were taught, but I don't know where he's going with this.
The person to solve this problem was Max Planck.
Right.
But Planck almost didn't make it into studying physics. Because when he was 16 years old, he went up to his professor and asked him, well, maybe I could do a career in physics. To which his professor responded that he'd better find another field to do research in, because physics was essentially a complete science.
Wow.
There was just a few tiny little problems that they had to clean up. But besides that, it was over.
But Planck didn't listen. By 1897, he was a professor himself, and for the next 3 years, he struggled to find a theoretical explanation for blackbody radiation. He tried approach after approach, but no matter what he tried, nothing worked. He said, "I was ready to sacrifice every one of my previous convictions about physical laws." Then, in a quote, act of desperation, he did something no one had thought to try. According to classical physics, the energy of an electromagnetic wave depends only on its amplitude, not its wavelength or frequency. And it could take any arbitrary value. So any atom could emit any wavelength of light with an arbitrarily small amount of energy. But Planck tried restricting the energy so that it could only come in multiples of a smallest amount, a quantum.
Right.
And he made the energy of one quantum directly proportional to its frequency, E equals hf,
H being a
where
constant.
h is just a constant. Think about what this does to the radiation coming from the black body. At a given temperature, the atoms in the cavity have a range of energies. Some have a little bit, a few have a lot, and most have their energy somewhere in between. For long wavelength, low frequency radiation, the energy hf of one quantum is small, so all of the atoms have enough energy to emit this wavelength, and the spectrum matches the Rayleigh-Jeans prediction very well. But at shorter wavelengths, higher frequencies, the energy of a quantum increases. And now, not all of the atoms have enough energy to emit that wavelength. This is why experiment diverges from the classical prediction. The spectrum peaks and then starts to fall, because fewer and fewer atoms have enough energy to emit one quantum of that radiation. And there comes a point when none of the atoms have enough energy to emit one quantum. So here, the spectrum must drop to zero. With this approach, Planck got a new formula for the radiation spectrum. Now, all that was left for him to do was to tune the parameter h, and when he did this just right, he got his formula to match up perfectly with experiment.
But he was sort of troubled by his own formula, because to him it was just a mathematical trick. He had no clue why it worked. It was purely formal, and most importantly, he had no clue what this h represented. I mean, he had introduced a new physical constant without any reason.
He wrote, "A theoretical interpretation had to be found at any cost, no matter how high." So from that moment on, he dedicated himself to finding one.
It's always fascinating looking on the other side of it, because to come to the conclusion that he wanted to, he came with a purely like mathematical solution to it, but did not have the theory to back up that solution. Which, I guess, sure, every mathematical expression is an expression of logic and understanding, but there are going to be expressions that just simply don't make sense. So I'm guessing his situation was, without theory you came to the solution, but you have no idea how to back that theory up. Fair enough, yeah.
He later reflected that after some weeks of the most strenuous work of my life, light came into the darkness, and a new,
The light of enlightenment, yeah, pun intended, nice.
undreamed of perspective opened up before me.
He introduces what we now call Planck's constant, and it has the units of action. Planck's constant h is a quantum of action.
Planck later proposed that anytime any change happened in nature, it would be some whole multiple of this quantum of action.
So it's kind of spooky. This breakthrough that starts the ball rolling toward quantum theory brings action in, not energy and not force, action. Gives you a hint.
At first, the quantum of action got little attention. That is, until a 26-year-old patent clerk came on the scene.
Well, Einstein.
In 1905, Albert Einstein claimed that Planck's theory wasn't just a mathematical trick. It was telling us that light actually comes in discrete packets, or photons, each with an energy hf. Einstein used this insight to explain the photoelectric effect, how light can eject electrons from metal, but only when the frequency is high enough. If the frequency is too low, no electrons will be emitted, regardless of the intensity. The idea of quantization spread. 8 years later, Niels Bohr was trying to understand how an atom is stable if it has a positive charge in the center and negative electrons whizzing around it. Why don't they just spiral into the nucleus, radiating their energy as they go?
Okay.
And what he wants to do is, he says there's something fishy about something being discrete. That seems to be the new ambiguous weirdo lesson of the new quantum of action.
Bohr realizes that as the electron goes around the nucleus, it has an angular momentum. Mass times velocity times radius. So angular momentum has the same units as action.
And so what he decides to do is discretize the orbital angular momentum for no good reason. He says, let me slap that on and say angular momentum of the electron can only be in 1 unit, 2 units, 3 units of the same quantity h. And because it's talking about motion in a circle, the factors 2 pi come in, so it's really nh over 2 pi, what we now call nh bar.
This comes out of nowhere. There seems like absolutely no good reason why angular momentum should be quantized.
I feel that is interesting, because I think the extent of what we were taught ends before someone tells us, oh, by the way, all these equations have this common concept of action. I feel like it would have been made more intuitive sense if it was taught like this, but I also understand why they didn't want to extend the syllabus. But that is interesting. But again,
but by doing it,
you have different levels. So I think when electrons jump from one level to a different level, only energy at that level jump is what's emitted out as light.
Bohr finds the correct energy levels of the hydrogen atom. When an electron jumps from a higher orbit to a lower one,
that much amount of energy.
The energy difference is given off as a photon of a particular color of light, exactly reproducing the hydrogen spectrum.
And that was a pretty startling thing to have fall out. I think that really was compelling. It takes some quantity with units of action and apply some, again, kind of ad hoc discretization or quantization to it.
Now, although it worked spectacularly well, no one could make sense of it. That is, until 11 years later. For his PhD, Louis de Broglie was contemplating the recent discoveries.
Oh my god, that's his name. Okay, what do you pronounce it?
For his PhD, Louis de Broglie was...
Brother, you have no idea how many students call him Broglie, okay? Louis de Broglie was basically how we called him, I'm gonna be honest. Not disrespecting the dude, but I'm gonna be real. Uncommon name, we're not used to it.
Contemplating the recent discoveries in physics, and his big insight was that if light could be both a wave and a particle, then maybe matter particles could also be waves. He proposed that everything, electrons, basketballs, people, absolutely everything has a wavelength. And he defined this wavelength analogously to light, as Planck's constant divided by the particle's momentum, or mass times velocity. Now, if an electron is a wave, the only way it could stay bound to a nucleus in an atom is if it exists as a standing wave. That requires that a whole number of wavelengths fit around the circumference of the orbit.
Okay.
You could have 1 wavelength, or 2 wavelengths, or 3, and so on. So the circumference 2 pi r must be equal to some multiple n times the wavelength. We can sub in de Broglie's expression for the wavelength to get that 2 pi r equals nh over mv. But we can rearrange this to get that mvr, the angular momentum, is equal to nh over 2 pi. That is precisely Bohr's quantized angular momentum condition. But now we have a good physical reason why it's quantized, because electrons are waves and they must exist as standing waves to be bound in atoms.
Because they want to have constructive interference of a stable orbit back. That's pretty good. You get a dissertation out of that. That's pretty good.
It is this wave nature of quantum objects that...
Wait, so they had to use... That is crazy, getting an explanation for a theorem that exists in technically the same field, but in a different specialty from a different specialty. It's kind of interesting. It's kind of interesting how all the sciences have different ways of understanding each other, but needing explanations from different places to kind of, fill in the gaps, which is cool. Nice.
Means they no longer have a single path through space. Instead, they must explore all possible paths.
Oh, wait, hold on a second. Wait, where did that jump come from? Hold on a second. Wait a minute.
Pretty good.
It is this wave nature of quantum objects that means they no longer have a single path through space. Instead, they must explore all possible paths. Now, I have thought about and taught the double slit experiment hundreds of times without fully realizing this implication. In the double slit experiment, I feel like the mental thing that I'm doing in my head is like, okay, well, the beam is not perfectly straight, and of course it's going to intersect both of those slits, because they're really close together, But then I heard this story about a professor teaching the double slit experiment, and it makes everything so clear. So the professor starts by explaining the setup. Electrons are fired one at a time through two slits to be detected at a screen. Now, because you can't say for certain which slit the particle went through, quantum mechanics tells us it must go through both at the same time.
Which itself is crazy. Which is crazy work. It's like, well, we don't know where the particle has gone through. Like, slit 1 or slit 2. But now, since it's a wave, we will assume they went through both. Is crazy.
So to get the probability of finding a particle somewhere on the screen, you simply add up the amplitude of the wave going through one slit with the amplitude of the wave going through the other slit, and square it. But that's when a student raised his hand. What if you add a third slit? Well, you just add up the amplitudes of the waves going through each of the three slits, and you can work out the probability. The professor wanted to continue, but then the student interjected again. What if you add a fourth slit and a fifth? The professor, who is now clearly losing his patience, replies, I think it's clear to the whole class that you just add up the amplitudes from all the slits. It's the same for 6, 7, etc.
Wouldn't, by that same logic, at one point do you keep adding enough slits where there's no longer just slits and just an open space? Like, at what point would it switch from being a particular expression on the other wall to a matter-like expression? Like, at what point does that distinction happen? Would be the ultimate question, I think.
But now the bold student pressed his advantage. What if I make it infinite slits?
Yeah, and you just keep doing that.
So that the screen disappears. And then I add a second screen with infinite slits, and a third, and a fourth.
Okay, I didn't go that far. Hold on, what?
The student's point was clear. Even when we're not doing a double slit experiment, when it's just light or particles traveling through empty space, they must be exploring all possible paths.
Wait, what?
Even when we're not doing a double slit experiment, when it's just light or particles traveling through empty space, they must be exploring all possible paths. Because this is exactly how the math would work if you had infinite...
Oh my god, he's right. It's just a wait, it's just clicking in my mind. Wait.
It's just light or particles. I add a second screen within...
Okay, so the argument wasn't whether or not you just keep adding enough slits so that the wall disappears. The logic would be that you keep adding more and more slits because you keep averaging the probability that as a wave it went through both the slits. So if you have infinite slits, it's considered infinite possibilities. And you keep adding more and more of them, it goes through each one, checking the probability for it. And then if you have enough of them that the wall itself is removed, since they're all slits, the wave should still be looking at the possibility of going, oh my... There is no way that is intuitively accurate. That can't be the case. Like, from what we've come so far, I understand it. But that is just like it goes against every intuitive like instinct. It's like that can't be the case. That nah. Nah, Femlab. I can't accept this. Now, that has got to be like the most insane deduction from physics. That's like, I can understand how the mathematical expression needs a logical grounding in reality, but what you just explained to me must be some form of like physical wizardry. Like that can't be the case. And yet the equations kind of back it up. Well, not kind of. They back it up. That's
infinite slits, and a third, and a fourth. The student's point was clear. Even when we're not doing a double slit experiment, when it's just light or particles traveling through empty space, they must be exploring all possible paths. Because this is exactly how the math would work if you had infinite screens, each with infinite slits.
So even in reality, it would be the case. But that it doesn't make intuitive sense. It just doesn't. Basically, that's like saying if you had like, I don't know, like I get it. It's like saying the whole thing with electrons, you can't really know their like the position and velocity at the same time. I get that. That's fair enough. I think there is an intuitive understanding there. But by that same logic, if you, it just doesn't make sense though, doesn't it? It's like saying if, for example, light takes all possible paths through space, the reason we see light going from point A to point B just so happens to be the case that it's the action of it's of least action, but also the highest probability that it goes from point A to point B. But if by that same definition that it's all probability, then there must still be some light going in like some weird different angles, even backward through time, because it has to go through all possibilities, right?
You have to add up the amplitude from each slit. That's just the way it works. According to the story, the student was Richard Feynman.
That actually makes sense. Yeah, I mean, okay. I'm not sure about the accuracy of the story, but if it had to be a student who asked the question, it had to be Feynman. Fair enough. Yeah. It wouldn't be bad.
And while the story is made up,
okay, yeah.
The logic is flawless.
Because if you believe in a double slit experiment, that you can't tell which of the two slits the particle went through, then you have to consider the possibility that it goes through both.
I just hate that it has to be a possibility. There is.
By that same logic, anytime any particle goes from place 1 to place 2, you have to consider all the possible paths it could take to get there, including ones that go faster than the speed of light, including ones that go back in time, and including ones that go to the sun and back.
Go through the sun and back. No, I get it. It's a quantum property, and there is obviously the way of saying that yes, in theory, it could be the case, but in practicality, it's almost never the case. I think that's the argument that we're going for here. I think.
I feel like it can't go to the sun and back. You have to restrict it to be local,
yeah,
right?
which would be like the most logical case.
So the math doesn't do that. I mean, you could see that just in the double slit experiment, right? And we'll do light, because then there's no funky business with the speed.
Okay.
If you're going to say, like, this path interferes with this path, then these distances are different.
Right.
And so clearly, they can't have the same speed. So you need to consider paths that have different speeds.
Feynman's way of doing quantum mechanics suggests that. So, according to Feynman, anytime a particle, a photon, or even a macroscopic object moves from point 1 to point 2, it has some chance to take any path. And as preposterous as it might sound, he found that we need to include all these paths in our calculation.
The way you define microscopic and macroscopic has got to be pretty important there, because by that same logic, that means if I throw a tennis ball in the air, there is somehow a non-zero possibility that at some point in the infinitesimally long future, that if I keep throwing that ball up in the air or it's from A to B, suddenly it just does not go the path it's supposed to and takes a random C route. Because there is a non-probable or like a non-zero probability it could take a weird-ass route. They could even go back in time, which is just... Brother, do you have any idea how insane that is?
Where each path is weighted the same. So why then do we not see all those crazy
No,
paths?
to be fair, that could be because the mathematics defining it that just the sheer odds of it not happening have not yet happened. Probably like in the entire age of the universe has not been long enough for something like that to happen, which is most likely the case.
Well, that's because we still need to add up their amplitudes.
Oh, okay.
For simplicity, imagine we only have 3 paths. Then here's what we're going to do. First, let's take this one. When the particle wave starts following it, we start a stopwatch. It goes around and around very fast, and when it gets to the end point, we hit stop. We'll do the same for the other 2 paths. And then we add up the arrows, square the result, and that is then proportional to the probability the particle took those paths to get there. In this case, the arrow and square are pretty small, so the probability of the particle going from 1 to 2 using these paths is small. Compare that with these 3 paths, for example. Well, now the arrow is much larger. And this is important. The larger the resulting arrow, the higher the probability of that event happening. Now, in these examples, the stopwatch is not actually measuring time. Instead, it measures something called the phase. Just as in the double slit experiment, when a wave takes a different path from point 1 to 2, it will end up there with a different phase.
Okay. And those phases could destructively interrupt each other.
This phase is what determines the amplitude of the wave at that point. Mathematically, we can write the amplitude, our stopwatch, as e to the I phi, where phi is the phase. As the particle wave follows a path, its phase increases, winding the vector around. So now the big question is, how much does the phase change for each path? Well, to answer that, imagine we split up the path into many tiny sections, each one so small that it's effectively straight. Then, in each section, the particle wave goes a distance delta x in a time delta t, and the increase in phase is easy to compute. It just depends on the wavelength and frequency of the wave. To find the total increase in phase for the whole path, we just add up all the little phase increases of all the individual sections. But we can sub in lambda equals h over mv from de Broglie, and using E equals hf, we can sub in for frequency. We can also simplify by writing h over 2 pi as h bar to get this expression. Then we can take delta t to the right, and if we make delta t infinitesimally small, then we can replace this sum with an integral. But now dx by dt is just velocity, so we can write this as mv squared. Now, we know that in the simplest case, the total energy E is just kinetic plus potential energy. And subbing that in, we're left with the integral over time of kinetic energy minus potential energy. But wait a second, that is just the classical action. So it's action that determines how fast the stopwatch turns. As the particle moves along a trajectory, its action increases, and that is what increases the phase. And what's important to note is that h bar is tiny. It's about 10 to the minus 34 joule seconds, which is way smaller than the action of any everyday object. That means the phase of ordinary objects on ordinary paths spins around zillions of times, eventually pointing in some random direction. If you consider a slightly different path, the action may be slightly different, say 0.01 joule seconds different. That doesn't seem like much, but divide it by h bar, and the arrow will spin around 10 to the 32 more times, so again, it will just point in some random direction. This is what happens to almost all of the possible paths, so when you add up the phases, they just cancel out, they destructively interfere. The only exception is for the paths closest to the path of least action, because these paths are at a minimum. So if you make tiny changes to the path to first order, the action doesn't change. And so for other paths that are very close to the path of least action, their arrows point in basically the same direction. They constructively interfere, and that is why those are the paths we see. This explains how light knows where to go. I mean, it doesn't. It just explores all possible paths. But the paths we end up seeing are the ones that interfere constructively. And those are the paths of least action. So really, this is how classical
we just went through, like, if I'm not wrong, 100 years of advancements in physics in like the span of 20 minutes. But that is the most. If I did not see the proof, like, look, I understand this theory, and I understand that there is logical backing to this, but I gotta see some evidence, bro. I'm gonna be honest. That is crazy, because if at the end of the day all possible actions are the highest probability of those actions taking place, and just so happen to find the area of least action to perform said action is just, brother, you're losing me a bit. I'm gonna be honest. I'm trying to keep up, but that is. So there is a non-zero probability that it could take a different, like, it could take weirder paths that are less likely to be seen, but it's not impossible. So there must be a way to, like, convince that there is a more intuitive way to see this. You feel me?
Classical mechanics emerges from quantum mechanics. It's why a ball follows the trajectory it does, and how planets orbit the sun. They don't really have a precise trajectory. Instead, everything explores all possible paths. It's just that massive particles have large actions compared to h-bar, so that only paths extremely close to the true path of least action survive, which is why...
By that same logic, I'm trying to think this through, brother. It's like really grinding my gears though as well. But that must be like some weird form of, like, there must be a way where it's like at high enough energy levels, or maybe like, because it depends on energy, right?
They're much more particle-like. If you go to much smaller particles like electrons or photons, the actions are much smaller, and so there's more of a spread in which trajectories they actually end up
This
taking.
makes sense, because you have like situations where you have like I think in actual physical phenomena, like you have like these chip conductors, like, when they're like making like these microprocessors really, really small, they've had problems when you get really close to like nanometer scales. You have electrons that should be in certain channels just jumping around certain like physical barriers, because they're so small that there is now a non-zero probabilistic chance it could just disappear and reappear on the other side, which, when I heard about it, was like, okay, that's probably the particle, like, nature of that, the wave nature of that particle taking effect. But this is saying there is a way for you to, like, kind of see that even light exhibits this property, which is the reason why the double slit experiment is the way that it is. And that's the reason that's the case is because light is taking all possible, like, routes, and just happens to take the one that's the most probabilistic for it to follow.
Now, you might say, I still don't believe
very much. The only reason I'm believing this is because there's got to be some way to, like, some way to, like, prove it mathematically, or some way that there's a physical phenomena in nature where it's indisputable that it's right.
Casper has this incredible demo that should convince you 100% that this is really how the world works.
Oh, you gotta be kidding me.
To do it, I've got a light, a mirror, and a camera. Now,
clearly we've seen this a million times, with a mirror right behind me as well. So it's like, where are we going with this?
Infinitely many paths that the light could take. And according to Feynman, we have to add up the contributions of each of them, including paths that go like this. Now, you might say he's crazy.
I'm not crazy. That's what happened. Another possibility is it could come here and go, or it could come here and go, or it could come where you'd like it to come and go, and it can go over here and go, and so on and so on. And these are all possibilities.
And every single one of these paths has their own little arrow. So what we can do is we can look at all those arrows and see where they line up. And so if I turn on this light, that's exactly where you see it reflect, so that the angle of incidence is equal to the angle of reflection.
Okay.
But now what I'm going to do is I'm going to cover up that spot so that we no longer see the light reflect. And then I'm going to prove that Feynman is right, that really light also goes like this. It's just that most of the time those effects are canceled out.
Okay.
Now, that sounds impossible, right? But let's zoom in to this tiny piece right here. Then we see all these different paths and all the arrows just go around and around in circles.
Yeah.
So when you add them up, they all just cancel out. But what if I cover up about half of them like so? Well, now when I add up those arrows, you suddenly do see a large resulting arrow. And so if I can somehow cover up this mirror in many, many tiny strips, then I should be able to get the light to reflect like this.
Well, to be fair, that's like a very miniaturized version of the double slit experiment. It's just, with a mirror, isn't it?
And I can do that with this piece of foil right here. On this piece of foil, there are about 1,000 lines per millimeter, and that should be enough to get this effect. So,
wait a minute. Oh my God. Wait. I think my brain is just melting. But wait a minute. So is the double slit experiment, showing that wave nature of light because it just so happens to disrupt the usual typical actions that should negate, like for example, light traveling through space should generally be because it takes the path of least action, so highest probability. But just because you break it up into individual spectrums, like individual slits, you now break the ability to average out those probabilities, and then it then shows light taking all these. Oh my God. So the double slit experiment is a way to to demonstrate light is showing the probability. Oh my God, wait, I don't even know how to formulate this. Wait. So the double slit experiment shows the probabilistic nature of the splitting of light. And what he's going to do is take a miniaturized version of the double slit experiment, put it right there, and since it breaks up what should be canceling out, we should not only see light reflecting there, you should also see different pathways of light take. Oh my God, no way. There is no way.
Turn off the lights. So let's see. I'm gonna turn it on in 3, 2, 1. We see it! We see it! Ah! That is so cool. It actually looks a lot weirder than I was expecting it.
That is crazy.
I was expecting more like one spot, but there's many, many spots where it's reflecting. Ooh, okay. Okay, and just to show I haven't been cheating you, right underneath
you can still see
is my finger. And even with the light on, we see the light reflect. And if we remove the cover, then what do we see?
You still see it split, obviously.
Yeah, we see exactly the normal reflection.
Oh, it is. Of course, right. You see the normal reflection of, oh my God, that's right. You see the normal reflection of the light that should be coming from here. But because of the double slits, which are breaking up the parts of where they should constructively and they should destructively, cancel each other out and should not be showing it. Just because you have the slits, it also demonstrates that light is taking all those other pathways. But it should,
where it's always supposed to go, which is right there. And then we've got now all these extra reflections, all these extra bits where the pattern just lines up. So very, very cool.
That's interesting because they're all the wave, it's part of the waveform. And then the parts that destructively interfere are all gone. But the ones that should be constructively are, bro, that is insane.
When I was talking about this with a friend,
this makes so much more sense for now in my mind the double slit experiment it's like complete. The understanding is a lot more it's now I could probably say okay.
He said, yeah, but you're using a diffraction grating. That's kind of
would be well, yes, but you're also using a diffraction grating to kind of show the way light kind of averages out the probability of existing. I can see why.
Because you get all these other reflections right now. And this light is just going in all this. One other thing I've been super, super curious to try. I also want to do this with a laser, where I shine the laser right next to it. And then if light does take every possible path, we should also see it
Oh, he's
come
right.
up.
He's right. It's light. It does come like I just realized. Well, he's not wrong. Light is taking all these pathways. Bro, having it done with the laser is crazy work.
It probably shouldn't
It probably would work though. If the
Actually,
logic behind this is right, it should work.
laser right over here. And we can
And let's be
see
real, it's on a YouTube video on YouTube, so I'm gonna guess it did work, otherwise it wouldn't be part of the video, but still.
when I shine it, it really
Yeah,
does
it's at
just
one
go
spot.
to one spot. And you can see where that spot is. It's right over there,
Right.
which is about the same place where we had our reflection. And you can also see right now, if we look at this view, that you cannot see the laser light at all, right? Like I could see the laser, but I have to bring it down all the way over here.
Yeah, but that's fine.
And then I'm able to
Yeah, it's
see
still
the light.
visible.
But if I just put it up here, you can't see the reflection. Now, what I'm going to do next is I'm going to put this foil, this magic foil, and I'm going to put it over here. Oh, and we can turn off this.
Okay.
And now let's see what happens when I turn on the laser. Wait. Wait. No way. No way. It works. It works.
Yeah.
Wait, what?
Yeah, it's not appearing as like a lot of waves, maybe because of the wavelength. So, but there are places where they constructively appear, and the foil is disrupting some of those places where it should be destructively interfering and removed. But since it is interfering and allowing it to appear, like it's like magic, like revealing the nature of it, like because you're disrupting how it would typically look to us, that's insane. This is where it's supposed to be reflecting, but the wave nature also tells it to like go through different pathways. So it is showing it up here as well. That is
Where the laser
that
is
is
going.
crazy. Not in one.
Oh my
Not one. You
God.
see two.
It actually works.
That is.
What?
That is crazy.
This is definitely the coolest demo.
And honestly, if I'm being honest, I think a demo like this should be shown in school, bro. I wish I'd known about this years ago, genuinely, because I think you'd have genuinely more interest in physics and in science if you kind of realize not only is your intuitive understanding of space and time probably wrong, which is fair enough, but also your intuitive understanding of light is fundamentally flawed. The double slit experiment through rote learning, just by hearting it, is one way of looking at the approach, but intuitively understanding what it is about is a whole different story. That is insane.
I've ever done. So what I was doing is I was holding the laser, and I can show you right now, I was shining it down like this,
And
way
it's
off,
still there.
and you could still see it reflect. But if I take this away,
It doesn't, because it's destructively interfering, it's just vanishing off.
Appears.
But just by doing this,
If
you're
I-
allowing some of them to reappear.
I put this back, it appears.
That's crazy. But also what is interesting, what I did notice,
Done. So what I was doing is I was holding the laser, it disappears.
right, what's fascinating to me is it's only appearing here twice. It's not appearing in different places. When he used like, I think the full light, like just a regular bulb, you saw so many different light rays. And I think that genuinely is the different possibilities all those light rays could take. But since a laser is a singular like focal, like, focus beam of light, it's rare for it. Like the possibility of it taking a different route is so low, but it still has possibilities of it going in these two places. That's insane. That is insane. That is insane.
Put this back, it appears.
So
Wow.
that shows really that we cannot get rid of the area which gives zero, that it really is canceling out, and if we do clever things to it, we can demonstrate the reality of the reflections from this part of the
Right, because to prove that there is other possible paths that light is taking, you disrupt the areas which are destructively canceling out those other possibilities, revealing the other possibilities that light took in its path, in its decision to take the path of least action, which is insane. That is crazy. That is actually crazy.
So light, and by extension everything, really does explore all possible paths. It's just that most of the time, the crazy paths destructively interfere. That's because the actions of nearby paths change rapidly. Now, I've studied physics for most of my life, and I feel like I never really appreciated how important action and the principle of least action are. But now I think I finally get it. And I finally get why if you ask theoretical physicists what they're working on, they'll rarely talk about energy or forces. Most of the time, they'll talk about action.
Nobody in particle physics approaches particle physics from a viewpoint other than least action. But we teach physics historically, and least action is almost like the new kid on the block for understanding physics. And so we build up to it. But in reality, I think life's a lot easier once you realize there's this underlying principle.
Oh, yes.
Because when you do, then all you have to do is write down the correct Lagrangian, so you get the right action, and out come the laws of physics. So you've got a separate Lagrangian for classical mechanics, for special relativity, for electrodynamics,
wow,
and so on.
It's a single mathematical framework that once you've learnt it, then you can apply it in different places in exactly the same way. The hunt for the theory of everything, right? The thing that will encompass all of physics. In reality, what people are asking is, what is this Lagrangian that can spit out?
It's always the meme of like mathematics when you're in school and it's all numbers. Mathematics when you reach college, there is no numbers. It's just gibberish. It's just not. Fair enough.
All of the laws of physics.
This would probably cause nightmares to some non-mathematics.
Really what they're asking. At the moment, we haven't really found that, right? Because we can sticky tape things together, but we don't know if that's the proper mathematical structure. So that's what people are hunting for.
Wow. Hey, this is a. I don't usually get the opportunity to react like Veritasium videos, but I will admit it. Brother, this is a well done video. I don't know what it is, because I think a video that gives you better intuition and understanding of some of the most fundamental particles in the universe. I'm super glad that this video is popular as it is, and I'll be honest, it's inspirational how learning about something that used to terrify me in physics gives a much better understanding of not only light, but about the nature of the world we live in. I think genuinely it's well produced. I think this is a video that should be shown in every classroom of every college student who's taking physics, because I think having an intuitive understanding of physics, it's not like saying, oh my God, it gives life meaning, but it definitely helps you understand the fabric of the reality we all exist in. So yeah, it's a super well done video and I enjoyed it. Hope you guys enjoyed the video. Like, comment, subscribe. I'll catch you beautiful bastards in the next one. Peace. Take care. Nice.